let's see a short video on oxygen measurements. Now, oxygen measurements, there are roughly 7 methods. Okay, let's see one by one. First is Clark's Polarographic Electrode. Second one, Galvanic Fuel Cell. Third one, Paramagnetic Oxygen Analyzer. Fourth one, Mass Spectroscopy. Fifth one, Photoacoustic Spectroscopy. Sixth is Raman Spectroscopy. And finally, we have a chemical apparatus which is also known as Haldane apparatus. Don't worry, let's deal each one in brief. Alright? Okay. Before that, oxygen electrodes are called Amperometric electrodes, and pH and carbon dioxide electrodes are called Potentiometric electrodes. So from the name itself, it's very evident. Amperometric means current inducing or current producing or using current, and potentiometric means voltage. Because it's a current electrode, there should be a cathode and a anode. And since a potential difference is present in potentiometric electrodes, there is only a measuring electrode and a reference electrode. There is no cathode and anode. Now, most common confusion is what is cathode, what is anode, which is positive, which is negative. A very simple way to understand that. Let's see here. Cations, anions. Do you see a plus symbol in cations? So this means cations are positive ions, which means anions are negative ions. Now, cations get attracted to cathode. So, cathode is a negative electrode, and anions, they get attracted to anode. So for negative ions to get attracted, it should be a positive electrode. Now let's go to the first electrode, that is Clark's Polarographic Electrode. Now, because these are amperometric electrodes and they have a cathode and anode, you have to remember what is the cathode and what is the anode in Polarographic Clark's electrode as well as Galvanic Fuel Cell. So only 2 electrodes you have to remember what is a cathode and what is an anode. Don't worry, I have a very easy way to remember. Now, here you can see Clark's Polarographic Electrode. Take the first 2 letters, C, C. So here we have a platinum cathode. Easy? Now, this is platinum cathode, and then for anode we have silver in silver chloride. Alright? Now, here a 0.6 volt is applied steadily, and there is a sensing circuit and display circuit. start again from Clark's Polarographic Electrode. Now let's see Clark's Polarographic Electrode. Now these are amperometric electrodes. You have to remember what is a cathode and what is anode in two electrodes, that is Clark's Polarographic Electrode and Galvanic Fuel Cell. There is a very easy way to remember. See, in the Clark Polarographic Electrode, take the first two letters C and P. So here we have a platinum cathode. So Clark's Polarographic Electrode has a platinum cathode. Then what is the anode? It is silver in silver chloride. So we have a cathode, we have an anode. Now what is the buffer? We have here is the potassium hydroxide buffer. So cathode, anode, a buffer and an oxygen permeable membrane. So we have to find out the oxygen content, right? So this membrane should be permeable to oxygen. One more thing, a very important differentiation between polarographic Clark's electrode and galvanic fuel cell is this voltage. A 0.6 volt has to be constantly applied for the functioning of this electrode. Now we'll see the reactions to understand it better. Now, when the oxygen first at the anode, a reaction happens, that is silver with chloride forms AgCl releasing 4 electrons. Now when oxygen crosses the oxygen permeable membrane and reaches the platinum cathode, oxygen combines with water and uses these 4 electrons to form AgCl and OH minus. So there is a shift of these electrons from anode to the cathode. So this shift produces a small difference or a flow of current. So this flow of current depends on, that is the flow of current depends on oxygen molecules. So the greater number of oxygen molecules, greater will be the flow and the subsequent reading recognizing that oxygen. Okay. Now halothane, to be remembered here, it gives a falsely high reading of PO2. So this can be prevented by using halothane impermeable membrane. That's it. Okay. And now coming to the lifespan of these. So this cathode has a lifespan of 3 years due to protein accumulation. The protein accumulation can be prevented by having a membrane around, but then it greatly reduces the response time. So that is not feasible. And also the silver anode tends to disintegrate over time. Now let's go on to the next. So let's tick this off. Gives a sense of satisfaction, right? So Clark is over. Now we are on to the next one. We have galvanic fuel cell. So there we had a trick to remember what is a cathode and anode. Here also same trick. Galvanic fuel cell, first letter G. So here gold is the cathode. Easy? All right. So here it's written as noble metal as cathode, which is gold. Okay. And what is the anode? Here we have lead as the anode. Again, the electrolyte solution will be potassium hydroxide. Unlike the polarographic Clark electrode, here we don't need to give any external voltage because this itself creates a voltage. That is why it's also known as a fuel cell. It fuels its own mechanism. That's why a voltmeter is kept to identify the voltage produced. Similar reaction, first reaction happens in the anode, that is lead. This oxygen plus plumbum, that is Pb, with hydroxyl ions produces Pb2O2H minus and electrons. Also, it's written here. So these two electrons. Now, when oxygen passes through this oxygen permeable membrane, it goes to the cathode, accepts these 4 electrons along with water to form 4 hydroxyl ions. Same way, there is a shift of electrons from the anode to the cathode. So that flow of electrons is directly proportional to the number of oxygen molecules. So the more number of oxygen molecules, the more number and the reading would be higher. The response time of this is 30 seconds. But it cannot be used for breath to breath analysis because the response time is 30 seconds, obvious. Now, here the reagents get consumed somewhere from 6 months to 12 months. So there, Clark electrode, we had roughly 3 years lifespan. Here it is 6 to 12 months. And this reaction is a temperature sensitive reaction. So to measure the temperature, here one more component is there, which is called the thermistor. And this thermistor measures the temperature, and in case temperature fluctuates, there is an external temperature compensation which is there in this electrode. Now, let's go on to the next, that is paramagnetic oxygen analyzer. Let's first tick it for satisfaction. Yeah. Now, we have the paramagnetic oxygen analyzers here. Now, what is a paramagnetic? What do you mean by the term paramagnetic? Usually, the gases that are attracted by the magnetic field are called paramagnetic. Oxygen is paramagnetic. The reason? Because of the presence of unpaired electrons in the outer shell. Other gases like nitrogen and all, they are called diamagnetic. That is, they are repelled by the magnetic field. Okay. Now let's understand the paramagnetic oxygen analyzer. So here there is 2 nitrogen filled glass dumbbells. So one is here, second one is here. And then they are suspended in a magnetic field. So this magnetic field here is the north pole and here is the south pole. So we have nitrogen filled glass dumbbell with suspended in a magnetic field. Understood? Now, there is a mirror which is present in between the glass dumbbells, which is attached to it. Now, oxygen is passed through this paramagnetic analyzers. When oxygen is passed through this analyzer, oxygen is paramagnetic. That is, it gets attracted to the magnetic field or it attracts magnetic field. Now, when oxygen is passed, this glass dumbbell tends to move. So when it tries to move, we tend to provide an external electric current to prevent that deflection. So when oxygen is passed, because of magnetic field, it tends to move the dumbbell, but to prevent the movement, we tend to give an electric current, because with electric current, we can produce a magnetic field that nullifies the magnetic field disturbance caused by the oxygen molecules. So with this deflection, how much amount of current is required would be proportional to the oxygen. Say if 100 molecules of oxygen is coming, an X ampere of current is required or milliampere of current is required. If there are only 10 molecules of oxygen, nearly 1/10 of that current would be required. So the intensity of current required to keep the dumbbells in null deflection is what is calculated for oxygen content or the oxygen concentration. How do you know the spheres are not turning anywhere? Simple. There is a mirror, right? Shine a light and see the reflection. If the reflection stays nil, then there is no reflection in the field. So that is why we have a light source here and a photodiode which sees the or captures the reflected light. It's a very simple paramagnetic analyzer. All right. Now, the response time of this is 0.1 seconds. It's very useful in rapid breath-to-breath analysis. Now, the disadvantage with it is water vapor tends to contaminate this and causes inaccuracies. Also, it is very bulky and expensive. All right. Now let's move on to the next one. That is mass spectrometer. Now, what do you understand by mass spectrometer? So concept is very simple. So we have a gas sample which is bombarded with electron beam. So after it's being bombarded with electron beam, it is accelerated through a channel where it's subjected to strong magnetic field. So a magnetic field is applied here. So application of this magnetic field would lead to splitting of the constituent molecules of this gas based on their molecular weight, and that is detected by a detector. Now you may ask, what if two substances have same molecular weight? Say nitrous oxide and carbon dioxide both have 44 as a molecular weight. What then? Then the substituent constituents of this nitrous, which is also a nitric oxide, based on the distribution of that nitrous, can be differentiated from carbon dioxide. Now let's move on to the next one, that is photoacoustic spectroscopy. Now, what is photoacoustic spectroscopy? In the term it is there. Photo means light, acoustic means sound, spectroscopy we just saw. So nothing here, it is just light is being converted into sound. It is similar to mass spectroscopy, only here an infrared source which is non-visible spectrum, infrared or UV, any one source can be taken, and it is converted to sound, and it is subjected to similar method and analyzed using a microphone. That is photoacoustic spectrometry. All right. Now let's go on to Raman spectroscope. Now, what is Raman effect or Raman spectroscopy? Very simple concept, just listen carefully. Now, when you subject a monochromatic light, as in a light of a single wavelength, towards a object, let it be any object, okay, what happens is the object's rotational energy or the magnetic energy or the torsional force or the electrical force, any one of this can be changed by this sample, because it is an energy source at the end of the day, right? A light, monochromatic light, is an energy source. So this can cause disturbance in any one of these energy source. As a result, once this gives off energy, the energy of the incident light comes down, which means a light with a set wavelength like X, now it would have been reduced to Y. With further collision with the molecules, it can reduce to Z, or with further molecules, any arbitrary number, and so on. So a single monochromatic light can be dispersed into a lot of scattered wavelengths which are of smaller wavelengths than the incident light. This scattering effect is known as Raman scattering effect, and this is the basis of Raman spectroscopy. This much is enough to understand what is Raman spectroscopy. All right. And those of you are brave enough, this is the actual Raman spectroscopy. So we have an incident light here, and then we have a Raman scattering light which goes to the detector, and this is how samples are being detected. There are various other terminologies here which is beyond the scope of discussion at this level. All right. Okay. So, oh, we are reaching the end of the topic so soon, huh? Last one, the chemical apparatus or Haldane apparatus. So it's an old apparatus. So it consists of a glass tube with a oxygen absorbing substance. All right. So a powerful oxygen absorber is pyrogalol or potassium pyrogallate. This was used and the sample was exposed to this substance, and this rapidly used to absorb oxygen. So how much ever oxygen was being absorbed, and that was analyzed mentioning the oxygen concentration in that particular sample. To analyze carbon dioxide in the same apparatus, potassium hydroxide can be used instead of potassium pyrogallate. This marks the end of the topic. Thank you.